Have you ever wondered how we first discovered particles smaller than an atom? Today, we will explore the cathode ray tube experiment, the discovery of electrons, and its impact on atomic theory. We will examine the tube's setup, how cathode rays behave, and J.J. Thomson's groundbreaking measurements. First, let's understand the cathode ray tube itself. It is a sealed glass tube with most of the air pumped out, creating a vacuum. Inside are two metal plates called electrodes, a negative cathode and a positive anode. When high voltage is applied, invisible, cathode rays shoot from the cathode towards the anode. These rays make the glass glow faintly when they hit it, revealing their path. Early experiments showed these rays traveled in straight lines away from the cathode. They also had enough energy to make a small paddle wheel spin, indicating they were made of tiny particles. J.J. Thomson then investigated the nature of these mysterious cathode rays. He placed charged electric plates near the ray's path, creating an electric field. He observed that the cathode rays consistently bent towards the positive electric plate. This deflection proved that the rays carried a negative electric charge. Next, Thomson applied a magnetic field using external magnets to the same cathode ray. He found that the rays were also deflected by the magnetic field. The direction of this magnetic deflection further confirmed the particles were negatively charged. By carefully adjusting the strengths of both the electric and magnetic fields, Thomson could make the ray pass straight through. He balanced the electric force pulling the ray one way with the magnetic force pushing it the other. This balance allowed him to calculate a crucial property of the particles: their charge-to-mass ratio. What he discovered was astonishing. These negatively charged particles were identical, regardless of the metal used for the cathode. Moreover, their mass was much, much smaller than the lightest known atom, hydrogen. This was the groundbreaking discovery of the electron, a particle smaller than an atom. This finding revolutionized our understanding of matter. It proved that atoms were not indivisible spheres as previously thought by Dalton. Instead, atoms had smaller, negatively charged components, the electrons. This led to new atomic models, like Thomson's plum pudding model, where electrons were embedded in a positive sphere. Imagine an electron beam travels through a magnetic field and an electric field. If the electric force pushes the electron upwards and the magnetic force pushes it downwards with equal strength, the beam will travel straight. Thomson used this balance to figure out the speed of the electrons and then their charge-to-mass ratio. If you observe a cathode ray deflecting towards the negative plate, what would that imply about its charge? A deflection towards the negative plate would indicate that the ray particles carried a positive charge, not a negative one. The cathode ray tube experiment revealed cathode rays are streams of negatively charged particles. J.J. Thomson's precise measurements led to the discovery of the electron and its charge-to-mass ratio. This fundamental discovery proved atoms are not indivisible and dramatically advanced our understanding of atomic structure. It paved the way for modern physics and deeper explorations into the subatomic world. Generate your own educational videos for free at eduvids.vercel.app.